Right, okay, well the last one has raised more questions than I expected, so and I've not even published it yet, so let's go back and have a look at the flywheel and point out the few points that people have raised already. Right, back to the flywheel. Right, the first question people ask is, why on earth does it not fit in that position as well? Okay, now we've been through the CAD system, we've twisted the CAD drawings around, and they fit absolutely on alignment, even with very high levels of magnification. So we put it down to the fact that the machine, we've used the best machine in the world. We went to the specialists in the UK, Aquajet, and we used their best machine, accurate to 0.1 of a millimetre, but even 0.1 of a millimetre, if you have 0.1 out that way and then the other axis is 0.1 the other way, you've got 0.2 already. So what we do is when we make the parts, we cut the left hand spiral and the right hand spiral from the same part of the bed on the machine. It's a big table, it's 4 metres by 1.5 metres. So we pick the same spot on the bed every time to do the same cuts. So even if we do it backwards, the machinery's any errors in the bed are cancelled out. So that's how we get it to work. So I think that really what happens is when we turn that round by a third, 120 degrees, there is that very slight difference because you're saying, well, what's the accuracy that way? Is it the same as the accuracy that way? So that's the only explanation we could come up with, and it seems fairly reasonable, and it fits in with the definition of the accuracy of the machine. So the machine is not perfect, it's the best you can do, but it's perfectly adequate if we allow for it to be locked in the same place each time, which is good practice anyway. Okay, so that's that one out of the way. Right. Now, how far do you turn the parts to fit? That was the second question. I've just got them written down here. Right, that's a good question. This is why we chose 3 spirals. 3 obviously locks in. I mean, 2 you can get a bit of a wobble, and 4 there's not enough movement. So we chose 3 particularly because we start off, as you know, with a 1.5 millimetre cut. Okay then, and the spiral, because it's 3 degrees and it's a certain diameter, is 4.4 millimetres cut there, so deeper. So it goes from there to there, is 4.4 millimetres. Now we only want to go 1.5 millimetres. So when we go around here, if we could go all the way around to there, we'd have to be 4 millimetres smaller, 4.5 millimetres smaller, 4.4 millimetres. So what we do, we turn it until the 1.5 millimetres gradually drops. And so it's a third of a third. So it's about 1.5 to 1.4, say a third. So we go a third down there, and it's a third of a turn. So that means that the flywheel can drop in over a good section of turn there. You just drop the flywheel anywhere in that area, and it will drop in. So it's got a nice movement. It's also got a large area of grip. We're not sort of moving up and just holding it in 3 places. It's still got 70% support, so it's not weakened it in any way. So basically that was why we chose it. So that fits in there, and that goes up there a 1/3 of a third, so a 1/9 of a turn. Okay then, so that's how we chose that. Now number 3. Oh, somebody just asked how we lock them in. Right, that's easy. I've got some bolts here, not quite right ones. But basically, if you want this to bolt onto the hub, now don't forget there's a hub in here on the flywheel, on the shaft. So this is the type of bolt I'm referring to. Now the hub, the thickness on that is not 16 millimetres, which you're going to use, but it's the principle. So we hone a hole in there, right through that piece. Now the beauty about it is that the more inaccurate you do it, the better, because there's 3 of them. And if we put them in different places in each one, then it will only fit together in one way. So it literally, we just hone a hole, approximate position there. We'll do it. We'll measure it, but it doesn't mean important as long as it goes through there and goes through part of the hub. And then the other side of the hub, is a nut. So that means that there's a honed shaft for 3 of them. One there, one there, and one there. Now, apart from the fact they're going to be a bit bigger because it's a big flywheel, that is the way the flywheel gets held on. Okay, now we could possibly use those to tension the flywheel against the hub as well, but I think we're going to need 3 more to actually bolt it down. Okay then, so that's that question answered. Now the last question's a really interesting one. Somebody said, have I damaged the flywheel by cutting out that stupid shape? And in fact the answer to that is yes, we have. Yes, we have damaged the flywheel. It won't rotate as fast. Right, now flywheel design is very, very interesting. If you look at this flywheel here, when it's spinning at high speed, everybody thinks that this is where the tension is. Okay, and it's not. The highest stress point is here, here, and here. Okay, now the reason for that is because imagine you've got a load of little men all holding hands, trying to hold this together and spinning them round. This is a shorter length of men here than there is around here. It's just a rough idea, but basically these men in the front end up with handling all the weight coming from here. So when this actually does expand a little bit, but the expansion is higher here than it is here. So what happens is the stress level here on the inside of the flywheel is higher than the stress level on the outside. Now this is contrary to everybody's expectations. I've even had real learned people telling me they're going to put a steel wire around the outside because steel's a high tensile strength and the wire is high tensile strength on the metal, so you can wrap loads of steel wire around it. And that is complete rubbish because the steel wire doesn't get any support from it inside and the solid material does. So the solid material will be able to spin at a higher speed than if you have a wire mesh at the outside, but even if it's completely wrap-wise. So basically, the solid material. Now, where do these numbers come from? The normal practice, I've seen it a lot in Germany. I think that's the way these were designed, because these were designed in Germany by Peter Krauss. To me, looking at the speeds and the size, I would say this is designed with a rim speed calculator, which says, let's imagine a thin rim at the outside. How fast could you spin it before the tension in the rim would be greater than the stress you're going to allow in the metal? Now that means that it's very conservative because it makes no allowance for this distance. Now if you get an American flywheel, you find quite 50% bigger, because the Americans use a formula in the Mechanics Handbook, 24th edition. Got a picture of it somewhere. I've got that one. I've got the whole book somewhere, but I can't find it for this purpose. They use that book, and in that book, it gives you a formula for working out the tension at this point here. It actually gives you it just gives you for here and here. It doesn't know this is here. But basically what you do is the tension in this is less than this. So you take this as a worst point, as if all this metal has been taken away. So you cut that out there in your paperwork and work out the stress in that point. Okay, so that will give you the worst stress in a worst situation when you've got less metal holding it together. So you use that formula and that works out that way. Now, where does the numbers come from? The engineer's handbook doesn't tell you. It just gives you a formula, and everybody in America uses it. The original formula came from Roark. I think it's an American magazine book actually, but nobody in America seems to read it. Right, so Roark's formulas describes the stresses in mostly static objects, but there are a few rotating objects, and one's a flywheel. And he gives you a mathematical calculation of exactly why the stress there is higher. And what's more, people have tested it. So people check the flywheel by building flywheels and find out if he's right. Now what happens is, an interesting thing happens. When you spin this flywheel, the first part of the metal to go over its elastic limit is the inside piece. So what happens is, that gets stretched. And then when you stop it again, when you stop it again, there's tension still in this back to front now, it's pushing it inwards. Okay? But it means that next time you pull it, this piece starts off by getting less tension in it, less pressure in it, and then more tension in it. So the actual theory indicates that it does actually break at the what you expect it to do, but this metal here tends to elongate. I mean, it's so small you can't measure it. Well, you might be able to now actually, but when they did, they couldn't do it. So the calculation is slightly conservative, because when the experiments were done, it was found that you couldn't tell where it was going to break, but this was the point where this is the tension where it broke. So you could actually, if you wanted to take advantage of that, you could actually run the flywheels a bit faster. But nobody's into the idea of pushing the limits to the limit. The calculation I'm using have been in the 24th edition since I bought my first copy in 1983, and so they're used widely, and so I'm using the calculation. There is a slight, you can get about 20 RPM more if you use Rock's formulas. I don't know where that came from, but we use these formulas because they're good enough. Okay then, so they're conservative. So that's the way the formulas. So we have actually damaged the flywheel by cutting into there. But as I said, the first thing I said was it's a German flywheel, and it's very, very conservative. So we've run the calculations on this. Even if this was S275, the weakest 275 newtons per square millimetre steel, it would have a safety factor of 8. So it isn't even worth doing an assessment, because it couldn't be worse than that. So this could be made out of any sort of steel. Even with those cuts in it, it's not reduced the stress significantly that it would be unsafe. So let's leave it at that. The flywheel is going to be safe. So I'll leave it if any questions about that. And I've dealt with at least the first 4 points. Now, if you've got any other questions, by all means put them in the comments at the bottom. That's what everybody says, isn't it? And then we'll add to them. Maybe we'll do a third version. Okay then, so that's it. I think that's the 4 points dealt with.